Unit 1.6, we're going to look at two separate topics. The first is going to be percent error, and then we're going to look specifically at states of matter more. We talked a little bit about it earlier in the video or the chapter. Percent error is a calculation that we use quite a bit to evaluate how well we did in our measurements. It's how close the measurement is to an accepted value. If you have low percent error, it means that your measurement was close to the accepted value. Here's an example that we're going to look at. The measured density of a sample of aluminum was 2.8 grams per milliliter, and if you were to look up the density of aluminum in a textbook or a reference manual, you would see that the density that's accepted is 2.7 grams per milliliter. We're going to find out what the percent error is. Now, the percent error is the accepted value minus the measured value, and you'll notice here we have these marks that indicate the absolute value, just how far apart the numbers are. And this is actually what we would call this part up here is what we refer to as our amount of error. It's how far apart our two values are. So the difference between 2.88 and 2.70, doesn't matter which one's bigger here, just how far apart they are, which is, of course, if you subtract that, it's 0.18. You divide it by the accepted value, which is 2.7. It's what it's supposed to be. Then you take that times 100. You end up getting 6.67% error. Now, a side note here is that each of these terms has 3 significant figures, so I have 3 significant figures in my answer. So again, close to 0 is a good percent error. It's a low value. Next, we're going to transition into states of matter. Matter is anything that takes up space and has mass. And here we see 3 different common states of matter. There's more than 3, but we really focus on these 3. We see solids, liquids, and gases. Solids are rigid and they have a fixed volume and shape. They may or may not be crystalline in structure. It depends on the substance. They're either crystalline, which means they have a repeating pattern, or they would be amorphous, which would mean that they lack a crystal pattern, but either way, those two things are solids. Liquids have definite volume, but no definite shape. You know this. If you pour a liquid into a glass, it takes the shape of that glass. And that's what makes a liquid a liquid. It flows, just like a gas also flows. It has no fixed volume or shape, and it will expand to fill the entire shape and volume of the container that it's placed inside of. Next, we talk about mixtures. Mixtures have a varying composition, and there's different types of mixtures. There's a homogeneous mixture, which has visibly indistinguishable parts. Another name for it is a solution. Like if you have sugar water, you can't see the sugar separate from the water. It's a solution. A heterogeneous mixture does have visibly distinguishable parts. Like if you were to mix up marshmallows into your hot chocolate, you could see the 2 separate pieces. Until, of course, those marshmallows dissolve, then you would have a homogeneous mixture again. Quick check on this. Which of the following is a homogeneous mixture, meaning that you cannot see the components? In pure water, I cannot see the components. So if I were to highlight homogeneous, this one, is it a mixture? No, because it is pure, so it's just a pure substance. And it's H2O, nothing else is in it, so this is a compound, not a mixture. So we can't have that one. River water is a mixture. Can you see things in it? Yes. This is a heterogeneous mixture. I bet you could see maybe some silt or evidence of some plant or animal life. So that's a heterogeneous mixture. Jar of jelly beans. Well, if you just have, let's say, red jelly beans, it would be just all the same kind of material. Jelly beans are a mixture of different types of flavors, sweeteners, I don't know, protein maybe. So that would be a homogeneous mixture. Soil would be a heterogeneous. There's definitely different components within the soil, plant and animal matter. And copper metal is a pure element. It's not a mixture at all. So I guess the best answer is the jar of jelly beans. So within matter, does it have a variable composition? Either yes, it varies, or no, it does not. So it's pure substances versus mixtures. And then are the parts visibly distinguishable? Yes or no. And does it contain various types of atoms? Yes or no. This kind of walks you through. This is a great flow chart to help you understand matter. Talking about physical and chemical changes, a physical change does not change the composition of a substance. An example is boiling or freezing water or any other phase changes. Below we see some other examples. We can use physical changes to separate mixtures into pure compounds, but it doesn't break up the compounds themselves into simpler pieces. Distillation, filtration, and chromatography are all separation techniques that rely on physical changes. Next, we'll be looking at chemical changes. In chemical changes, we have a new substance, or maybe new substances, with different properties and different composition. So if you have a Bunsen burner, we would have methane. Methane is CH4. It reacts with oxygen, which is O2, to form carbon dioxide and water. So we start with these two, and we end with these two. Totally different substances. So we do have a chemical change. Let's see if this clicks for you. How many of the following are examples of a chemical change? Let's use C for chemical change. If we crush rock salt, that just makes the pieces smaller. That's just a physical change. Burn wood, we get new things like carbon dioxide and water vapor and maybe some soot. So that'll be a chemical change. Dissolving sugar, just as a physical change when you dissolve, because it still is sugar, it's still water, just mixed together. And melting a popsicle on a warm day, we just melted as a physical change because it's a example of a phase change. So we just have that one answer there that is a chemical change.